So we have the surface area of the leaf. So this is going to be 40 times, rather we can say, we'll call it A absorb. So this will be 40 times 10 to the -4th meters squared. We have a theta of 0 degrees, and then we have the Stefan-Boltzmann constant of 5.67 times 10 to the -8th. The units for this will be watts per meter squared times Kelvin to the 4th power. And we have an initial temperature of 308 Kelvin, and then we have a T2 of 297 Kelvin. So we have the specific latent heat of vaporization. So this will be 2,450 kilojoules per kilogram. And this will be at T equals 20 degrees Celsius. And we have the solar constant equal to 1,000 watts per meter squared. And I think we can start the problem by saying the rate of heat flow of the solar heating is going to equal the rate of heat flow of the radiation plus the rate of heat flow of evaporation. Now we can say that for solar heating, the formula becomes 1,000 watts per meter squared, and then we can say times epsilon, the emissivity, times A absorb, times cosine of theta. This is going to simply equal 1. And this will equal epsilon sigma A radiate T sub 1 to the 4th minus T sub 2 to the 4th. And then it'll be plus the mass of water times the latent heat of vaporization times delta T. So we can say that the mass of water per delta T is simply going to be equal to epsilon A absorb 1,000 minus 2 sigma T sub 1 to the 4th minus T sub 2 to the 4th all over the latent heat of vaporization. So now we can get a new workbook and solve. So the mass of water divided by delta T is going to be equal to 0.85, the emissivity, times 0.004 meters squared. That's going to be the A absorb, 1,000 solar constant, minus 2 times Stefan-Boltzmann constant, 5.67 times 10 to the -8th, times 308 to the 4th minus 297 to the 4th, all divided by the latent heat of vaporization. So this will be 2.45 times 10 to the 6th joules per kilogram. And we find that this is going to be equal to 1.196 times 10 to the -6 kilograms per second. We can multiply this by 1,000 grams for every 1 kilogram, and then we'll say 3,600 seconds for every 1 hour. And we can say that this is going to be approximately 4.3 grams per hour H2O lost. This will be our final answer for this problem. That's the lost. That's the end of the solution. Thank you for watching.